In this theorem, we are going to show that addition makes sense modulo m. So let me just motivate this theorem real quick. Suppose we're working in Z modulo 5, and I want to add the equivalence classes 0, maybe not 0, let's make it a little more interesting. Maybe I want to add the equivalence class 1 to the equivalence class 4. So naively, I would just add the 1 and the 4 to get a 5 and hope it works out. And I know that 5 and 0 are the same. But what if someone else didn't like using 1 to represent the equivalence class? What if they liked using, I don't know, negative 4? These are the same thing modulo 5. 1 minus minus 4 is 1 plus 4 is 5. So they're the same thing. And what if instead of 4, they wanted to use, say, 9 as an example? Or let's use something bigger. Let's use what's congruent. Let's say 14. These second two are also the same. So as elements of Z mod 5, they are just honestly equals on the nose. Well, if we want a well-defined addition, it shouldn't matter what our representative of the equivalence class is. We should get the same answer. So negative 4 plus 14 is negative 4. We'd imagine you just add these. Negative 4 plus 14 is 10. So this is equivalence class of 10. Is that the same as 0? Yeah, it is. Now, notice there is something that is actually special to this congruence modulo m. We don't get the same answer. When we added them before, we got 5 and 10. Those are not equal integers. However, they are the same in the same equivalence class or congruence class. So if we want to define addition modulo m, that is, if we want to look at arithmetic in this weird set Z mod m, then we would hope that the addition comes from normal addition, firstly. So we hope that addition is the normal one. Where I'm going to put usual in quotes, meaning I just mean comes from the addition in Z. But there's a well-definedness problem. So the main question here is, does this even make sense? Because we're dealing with equivalence classes, and as a meta principle, whenever you're dealing with equivalence classes, you always have to worry about if an operation is well defined. Okay, so does it even make sense? Is it well defined? And in this example, the naive approach ended up working, and in fact, that's what the theorem is saying. It's saying that if you took two guys that were congruent modulo m, so that is they're in the same equivalence class, like 1 and negative 4, so 1 is congruent mod 5 to negative 4, and another pair that were congruent modulo m, say 4 and 14, and m was 5 in that case, then their sums are still congruent modulo m. The sums are in the same equivalence class. They're still congruent. So that's what the theorem is trying to say. So let's prove the theorem, and hopefully this will give you an idea of how these proofs go. So let me just write down the hypotheses real quick. So we suppose that A is congruent mod m to C, and B is congruent mod m to D. And then we show that A plus B is congruent mod m to C plus D. Okay, just quickly copying down the hypothesis, what we're assuming, and our conclusion, what we're trying to show. All right, so let's write out what our hypothesis is telling us. So since A is congruent to C mod m, and B is congruent to D mod m, we have that m divides A minus C, and m divides B minus D. Now let's write out the definition of divides. Thus, there exists, well, okay, let's not actually write out the definition of divides just yet. I'll do an alternate proof where we do that way. Now let's write out what we want. So we want to show A plus B is congruent to M mod M to C plus D, which is equivalent to, this is just the definition, M divides A plus B minus C plus D. And this is saying M divides A minus C plus B minus D if we distribute that negative through and then associate terms. And now I'm going to remind you that you prove the 2 out of 3 property. So let's just notice that M divides A minus C, M divides B minus D, and A minus C plus B minus D seems to be equal to A plus B minus C plus D. So M divides this term, the first term, M divides the second term, so M must divide the third term. So since divisibility satisfies this 2 out of 3 property I keep mentioning, we know that it must divide this this expression here. And that's all we wanted to show, okay? Because that will tell us that M is, well, I guess we wanted this expression, the equivalent one, A plus B minus C plus D. And that tells us that these guys are congruent modulo M. Now, alternatively, we could have been a little bit more verbose here. So we could continue with we suppose and then copy in the supposition, we show, and then copy in what we want to show. And then we could say since A is congruent mod M to B, or to C rather, and B is congruent mod M to D, there exist integers K and L such that A minus C is MK, that is M goes into A minus C, and B minus D is ML, that is M goes into B minus D. Thus, A plus C, or A plus B rather, minus C plus D is again A minus C plus B minus D, the same thing as before. Now, our A minus C we can replace with MK, and our B minus D with ML. And that's MK plus L. And so what do we conclude from that? We conclude that, well, M must divide the left-hand side. Now, again, all we're doing here is we're reproving the 2 out of 3 property, but if you're not comfortable with that, you can always go ahead and write out all the definitions. So M divides this expression, and so A plus B is congruent mod M to C plus D. That's just the definition of congruence. So addition is a well-defined operation on Z mod M is what this theorem is saying.